Um, so today is a really nice day. You learn everything about multiple population, stellar population in globular clusters.
Thanks. So the first two lectures, we set the frame to understand what what are globular clusters, and now we will look to this issue of the multiple stellar population if I succeed to go down to the next page. Okay. At first glance, the color magnitude diagram of a globular cluster looks as an isochrone. And so one thinks that it is a good approximation to a single stellar population. However, even in a very first look, one should immediately see something very strange, because in an isochrone, the horizontal branch should be very, very short, should be actually essentially a point. So why it is so extended? Because the extension of the horizontal branch is essentially an extension in mass. So you see different masses of the object. And why there are different masses of the object evolving in such a short time, like the lifetime of the horizontal branch. So this is a thing that should be noticed immediately, and in fact it was. But since it was not understood, the people didn't care too much. Many concepts of stellar evolution were developed, try to explain the location of stars in the color magnitude diagram of globular cluster using the single stellar population concept. So ideas like the nature of the blue stragglers, the need of the inclusion of mass loss in the stellar models. This is what we see yesterday about our Lyre. The first direct evidence of mass loss from stars came from the observation of our Lyre in globular cluster. How you have to explain the branch, most aspects of the AGB evolution, the evolution of stars along the white dwarf cooling sequence, transformations between theoretical and observational plane, a lot about population synthesis in galaxies and so on. These are all based on the idea that the clusters are simple stellar populations. So it's a very clearly a very useful concept. But as many other approximations, when you begin to look into the details, it fails. Some sort used for all kind of approximation. If you make an approximation, of course, there may be some departure from this. But the case of this globular cluster, the departure from the single stellar population approximation is much larger and more significant than simply the fact that there is a small spread in some quantities like the formation epoch or some original inhomogeneities in the chemical composition. I announce these two facts, the fact that actually galaxy cannot be reproduced by simply summing up globular cluster. And furthermore, multiple stellar populations in globular cluster provide a clue on how they formed and likely on the relation they have with the host galaxies. So they are very important to be understood. Evidence for multiple stellar populations are very old. From spectroscopy, we knew since the early 70s that there was something strange in globular clusters. There were stars that occupy more or less the same position in the red giant branch. They have very different spectral features. From the definitive observation, however, was in 2001. The fact that we observed the sodium-oxygen anticorrelation on the main sequence of the globular cluster. This was the definitive evidence that there are multiple generations of stars in globular cluster. There were, however, other evidence, also of photometry, and actually this issue of the corner of the horizontal branch, the so-called second parameter, is an evidence for the multiple population, and it was evident from mid-60s, so more than 50 years ago. But it was not understood for a long time. We will see later why it was not understood, because it is a complicated issue, not because the people was not good. The second part is, the second evidence was about omega-10, the Woolley paper in 1966, the color-menu diagram of omega-10, showing a very broad giant branch. But omega-10 is a peculiar globular cluster, very interesting, but I will not have time to discuss in my lectures about omega-10. Then in the 70s, there were beginning to add other clusters, like NGC 2808 or NGC 1851, that have peculiarities, but still they were considered a peculiar cluster, not a general effect among globular clusters. The evidence, photometric evidence, clear photometric evidence came with HST, with multiple main sequence and subgiant branch, and this requires exquisite photometric precision. These are the first evidence, I think, from spectroscopy. This observation by Osborne in 1971, this was from DDO photometry, but later there were observations from spectroscopy that you have stars that are similar, but they have these are very similar stars in temperature. They have very similar, this is the calcium K line, but this is the CN band in 38, 23, and it's very different between these two stars. They are very similar from many points of view, but not from nitrogen abundance. It was quite soon understood that sometimes you have bimodal distribution along the red giant branch. This is work made by Norris and Smith, but many other contributors, especially Australian people. And they found this kind of distribution, of bimodal distribution, in the strength of this band here. In the 90s, the same work was done also for stars on the main sequence in 47 TAC, and it was found that, again, there is a spread and possibly an anti-correlation between carbon and nitrogen. But the very first clear evidence came from the sodium and oxygen abundances. Most globular clusters are really not homogeneous also for these elements, which are much more difficult to produce than carbon and nitrogen. Carbon and nitrogen may be altered simply by the CNO cycle. But to produce sodium, you need to overcome a non barrier, which is quite significant. And so this is an evidence that you need the high temperature. And this is, for instance, in this plot, we have two stars in the color menu diagram of NGC 2808. They are one twin of the other, apparently. But if you look at the oxygen line is very different in these two stars. So the abundance of oxygen is very different. And in general, it was found that there is an anti-correlation between the abundances of oxygen and the abundance of sodium. This was a work made by the Lick Texas group, Chris Needham, Bob Kraft, and others, that found this clear anti-correlation between the abundances of these two elements. How it is generated? Well, there was the work by Denisenkov and Denisenkova by Langer that found that at a temperature of about 30 million degrees, you have a complete CNO cycle. So not simply carbon and nitrogen abundances are changed, but also the oxygen abundances are changed, and you go to the equilibrium value for the CNO cycle, where almost all CNO comes into nitrogen, with only a small fraction, small part in carbon and oxygen. But at the same temperature, you may activate a neon sodium cycle. Actually, it is capture of a proton on neon 22 to produce sodium 23. This occurs at about 30 million Kelvin. Soon later it was discovered that there is also a magnesium-aluminum anticorrelation, and this requires a higher temperature, something of the order of 50 million Kelvin to be activated. So you need very high temperature. These are absolutely not possible on the main sequence of small mass stars. So, since there was some suspicion that there may be some mixing effect that can affect this result, the idea was to observe this sodium and oxygen anticorrelation, look for this sodium-oxygen anticorrelation on the main sequence, where mixing cannot be effective. And it was found, we did as soon as UVES, the spectrograph on, of the VLT spectrograph on the 8 meter, we tried to do this job, and we made a large program. They assigned our time, and we could do this experiment to look if there is really an anticorrelation of sodium and oxygen. And we found it. This kind of anticorrelation, which is very similar to what is found in giant stars by the previous surveys. So the result is that essentially we found that this sodium anticorrelation is present also in the main sequence of the star, and we also found that there is a magnesium-aluminum anticorrelation, at least in GC6752. Clearly, this temperature 30 to 50 million Kelvin are too high to be found for main sequence stars, so internal mixing was ruled out. So this effect is something that cannot be created within the star where we observe this oxygen-sodium anticorrelation. Should come from previous generation of stars, and the stars that we observe are built on the products of this earlier generation. Another important fact was that these papers and the paper by Judy Cohen, Michael Bliley, Peter Stetson, showed that the spread in the abundances that we found in main sequence and subgiants are very similar. Now this is important because you have to think of that when you go from the main sequence to the subgiant, there is a deep penetration of the outer convective envelope. In the main sequence, the outer convective envelope takes only 1% of the mass, or something like that, for this kind of stars. While for the red giant branch, it takes almost 50% of the mass. So if you observe the same anticorrelation in two cases, it means that at least 50% of the mass of the star should be involved, but then it is easy to think that it is the whole star it is involved. It's not only a superficial effect. The stars are completely done in this way. And this shows clearly that the effect not only is of a two generation, but the second generation was brought from the ejecta of the first generation, not simply polluted by the ejecta of the first generation. This was the situation in about 2007. It was recognized that there is this anticorrelation, that globular cluster hosts a different generation of stars. It was not clear if it was a common effect to all clusters or simply some of them show this effect. And, but in any case, what was found is that there is no detectable production of iron and heavy elements in most of the clusters. There are a few exceptions. So we started a survey with Eugenio Carretta and Angela Baragaglia and Lucatello to observe a large number of clusters, trying to understand if this sodium anticorrelation is really widespread, how it changes from cluster to cluster, what is their characteristics. And we observed about 20 clusters, and we found that the sodium-oxygen anticorrelation is present everywhere. In all the clusters that we examined, there is the sodium-oxygen anticorrelation. This is a basic result that has been confirmed by many others. For instance, these are the clusters that are in the Apogee survey. these are near-infrared observation. You cannot obtain the oxygen abundance. In the apogee wavelength, you have only magnesium and aluminum lines. But again, you find that there is a very widespread anticorrelation. So magnesium and aluminum are not anticorrelated in some clusters like M71, but in most of them they are. Many other papers. In some clusters, the sodium anticorrelation is absent, but these are systematically low luminosity objects. The brightest cluster so far where there is no evidence of the sodium-oxygen anticorrelation is Ruprecht 106, which has a apparent magnitude of -6.3, and all sodium-oxygen anticorrelation was not found. They are very faint. We may then look at the clusters in a absolute magnitude. Well, we put here relative age. It is probably important, but in this moment, say is another axis. And in this plot, we have all the clusters. These are all the globular clusters known. And the empty circle squares are simply clusters not observed. The red ones are the clusters with the sodium-oxygen anticorrelation. The green ones, or blue, I don't remember the color of what it is, are the clusters where there is no evidence for the sodium-oxygen anticorrelation, but they have been observed. So they have been observed. And you see that there is a clear trend. All the luminous cluster have the sodium-oxygen anticorrelation. Less luminous do not have. A couple of examples like PAL5 and NGC 6535 are evidence for mass loss. PAL5 is the cluster with the tidal tail that I showed yesterday. NGC 6535 has a very peculiar luminosity function, is also very likely to be a cluster with a loss of mass lost. So the cut probably is something here, at about 210 to the 5 solar masses.
I see also the age things, yes. So there is a cut even stronger in age, it seems to me. How do you express that scale?
Relative age is an age in which 1 means the older. And 0.6 should be roughly proportional to age. This scale was introduced to avoid problems with the absolute ages. But you must think here about 13 billion years and here about 5-6 billion years. By the way, this object here, for instance, and also this one, these are not globular clusters, these are open clusters, all open clusters in the galaxy. All globular clusters show. The open clusters do not show. There is a threshold in mass, and this threshold in mass should be around 210. Change again? The threshold in mass should be around 10 to the 5 solar masses, something like that. It's difficult to say because this is the current mass of the clusters, not the original mass of the clusters. And as we see yesterday, there are a lot of mechanisms of cluster destruction that cause mass loss from the cluster. So it is not clear what was the original mass of the clusters.
Yeah, but if, probably if you can go back to that one. So all of those that younger are open clusters or not?
Well, PAL12 is a cluster which is classified as a globular cluster. It is a cluster in the Sagittarius dwarf galaxy. It's difficult to say what it is exactly is, if it is a globular cluster or an open cluster. It's a matter of definition. But typically it's put in the list of the globular clusters.
This very important, yes, and also there is something that it's not clear, because the problem, elliptical will show you the opposite. So the one that seems to have a higher sodium abundance are also the one with higher oxygen abundance, so the most metal rich. Okay? If you said that there is stars evaporation in globular clusters, I have to point, how do you determine the sodium abundance, which will be emphasized in the dwarf stars that you might not have there because they have evaporated away? And wait a second, and if you detect multiple population using other lines and not only sodium?
The abundances are measured star by star. So in each star we do a spectrum synthesis analysis using model atmosphere and determine the abundances. So the sodium abundance are determined from many sodium lines, all that are available. Including near infrared, yes. Depending on the cluster, depending on the situation, depending what is available, it is used. Okay? And for what concern, the other question was? No, there is also magnesium and aluminum, and as I told you before, most of the clusters show magnesium, aluminum, but not all. There are clusters that have sodium-oxygen anticorrelation, but looks homogeneous in sodium and in magnesium and aluminum. For what concerns the iron, I said that the clusters are typically very homogeneous in iron. This is not true for all clusters. Most of the clusters, the vast majority, are homogeneous in iron, but the most massive ones have spread in the abundance of iron. This is more or less the observational error, and you will see that most of the clusters are here. So the spread in abundance is compatible with observational errors. By the way, the spread is very small. This is only 0.02 of a dex. So it's only 5% in abundance variation. So these clusters are really homogeneous. And this includes the observational error. If you keep out them, it's essentially zero. But the most massive ones show spread in abundances, also of iron. Okay, so I have said that the sodium-oxygen anticorrelation is general. All globular clusters show, but they show in a different way from cluster to cluster. These are the sample, two clusters. One is M4, NGC 6121. The other one is NGC 2808. Both shows a sodium-oxygen anticorrelation, but you see that the two distributions are quite different. In the case of M4, we have a quite steep distribution with only a small variation of oxygen, with a quite large variation of sodium. While in NGC 2808, we have a wide variation in oxygen and also some variation in sodium. Note that these all are upper limits. We don't know exactly where these points are. They should be somewhere here. This is likely related to the kind of polluters that gives the elements that we see, the composition that we see. For instance, if you consider the model, the AGB intermediate mass AGB stars, we have that the production of oxygen and sodium on the whole seems correlated each other. You produce more sodium where you produce also more oxygen in the AGB stars. But there is a variation with the mass. So if you take a 4 solar mass star, it gives higher sodium and oxygen. And if you take a 6 or 7 solar mass star, it gives a much lower production of sodium and actually a clear destruction of oxygen. And this is for aluminum and iron. In this case, only the stars essentially above 5 solar masses really contribute. The other ones produce very little of these quantities. how to explain the fact that we see an anti-correlation, sodium-oxygen, while the single element star produce a correlation between sodium and oxygen? Well, this is typically explained as a dilution model. That is, you start from a composition which is essentially the pure ejecta of the AGB star or something, or the polluter, and then you begin adding pristine material which has not passed through this nucleosynthesis in the polluter. And if you add them, you begin adding, and you begin to follow this curve. The curve comes because these are logarithmic diagrams, not linear diagrams. This is the reason it is a bumped curve and not a linear one. But essentially what you found is that they have, depending on the dilution, we follow this law. So essentially, what it's telling you is that you start from a different original composition. That means a different mixture of polluters, different typical mass of polluter in the different clusters. But then in all clusters there is this dilution effect. There are stars that have almost exactly the pristine AGB ejecta composition, and stars that have essentially the pristine composition, with a mixture of these two. In this model we can abstract the original composition essentially from this group of stars that are here. The stars that have zero contribution from the polluter, and all the composition from the original one. And actually what we found is that if we consider star here, in this part of the diagram, the composition of these stars is essentially indistinguishable from those of halo metal poor star, normal halo metal poor star. This is shown here for oxygen, and this shown here for sodium. So the maximum oxygen and minimum sodium, this point position here, reflects the position of the halo stars, field halo stars. And what is peculiar in globular cluster is this part of the population, what we call the intermediate and extreme, where there is this sign of pollution, the second generation are really different from the original ones. 0.2, 0.8 is the fraction that you have to take from one group from metal from one composition, and the fraction that you may take from the other, that has the other composition. Fraction of the mass of the star that you... No. This is, each star has a position in this diagram. And depending from on the position, we may have said that, for instance, a star that is here has some like 85% of the mass that come from the ejecta of the polluter, and 50% is pristine.
Action in the first, because this is like a mini galaxy.
We will go up because this is one of the next arguments. Now that we divided the stars now in 3 groups, which we call extreme, intermediate, primordial. I will come back on this because it is important in this context. Okay, we may define several quantities to quantify the spread of the anticorrelation. Which is important because if it is very compact, means that we have a small contribution by the second by polluter. If it is very extended, it means that there is a lot of contribution from the polluter. And this is done typically using the interquartile range. The advantage of the interquartile range, which means that there is 25% of the distribution here, 25 here, 25 here, and 25 here. And this quantity is not very sensitive to outliers, and this is the reason it is used. But this is a way to define the spread. It is not the only way. You may use other ways if you prefer. And we also use other indicators. However, if we use this indicator and use interquartile in the ratio oxygen to sodium, we found that there is a correlation of this quantity with the absolute magnitude of the cluster. The most luminous is the cluster, the more extended is the anti-correlation. And actually there is a second parameter that also governs this relation, which is the concentration of the cluster. The highest, the lowest the concentration of the cluster, actually the largest is this residual around the distribution. That is, you can set a line here, look at the residuals, and you see that this is the correlation around the residual. So if you want to do, for instance, a multivariate analysis, you discover that there are two parameters that are needed to explain the distribution. Another characteristics of this sodium-oxygen anticorrelation is that is strictly correlated to the maximum temperature that you can get on the horizontal branch. The stars that are, this is the hotter star that you have on the horizontal branch. This is the log of this temperature, may arrive in this case to, in some case to 40,000 Kelvin, 50,000 Kelvin, something like that. And this happens only in clusters that have a very extended oxygen-sodium anticorrelation. In clusters that do not have a extended sodium-oxygen anticorrelation, the horizontal branch is much shorter, much more compact. Well, this is another way to say the same thing because we use the minimum abundance of oxygen, which is also a measure of the extension of the anticorrelation. And is correlated with absolute magnitude. There is also, if you make a multivariate analysis, there's also a term which depends on metallicity. Okay, so it's clear that there is a variation from object to object, and this variation is related to the absolute magnitude of the object, probably also to metallicity and some other parameter, but mainly to the luminosity. We used another way to define the distribution, which is different from the interquartile, and it is dividing the star in three groups, which we call P, I, and E. The first group, P, is essentially the group of the stars that have more or less the same composition as the field stars. Okay? This is defined in a little bit odd way because we started from the lower part, then we added 4 sigma of the individual, 4 times the error in the determination, and stopped here. Okay? This is the idea. The idea behind is that if you take about 100 stars, the distribution more or less extends between plus minus 2 sigma. This is what is typical in a Gaussian distribution. So this is the way we define the P stars. Then the distinction between I and D stars is a little bit arbitrary, set here, and essentially corresponds to the fact that in some cluster you see really 3 populations, 1, 2, 3, but it has no very strong significance. But what essentially means is that the E stars are more extreme cases. The IK stars are less extreme cases of the sodium-oxygen anticorrelation. B should have more or less the primordial composition. Blue are upper limits in the oxygen abundance. Oxygen is much more difficult to determine than the sodium because the lines of oxygen are very weak. We are using a forbidden line of oxygen to determine the abundance of oxygen. This is very weak and not easy to determine the abundance, so in many cases we have only upper limits. No, these are all red giants in this case. But we know that red giants and main sequence stars distribute in the same way. When we tried to do the comparison, we found this. Okay, this is the distinction PIE for all the clusters in that survey. And we may count now the number of stars. This is your question. How many stars are in the different groups? And essentially we found that the primordial population in this group of clusters is more or less constant at about 30% of the stars. So 30% of the stars more or less have the original composition. The remaining 70% of the stars have an anomalous composition. Okay? The fraction of E stars is strongly dependent on the absolute magnitude. Okay, these are the brightest cluster, these are the fainter cluster, and the E stars are essentially present in the very bright clusters, not in all bright clusters. There is some cluster which is very bright and have quite low fraction of E stars or even nothing. This is 47 Tucane. And there is a correlation between, anti-correlation between the fraction of E and the fraction of I stars. That is, the P stays constant, so this changes essentially because you change some I into E when you go up in luminosity. Well, but there are more important facts. Another very important fact is that if you change in some way the sodium abundance, you expect also to change the helium abundance in some way. This is an important consideration because it leads to another family of consequences on the multiple populations. One important fact is that helium-rich stars that are more rich in helium than normal, evolve faster on the main sequence. This is essentially because they have less hydrogen, so the central temperature should be higher to compensate for the pressure, to give the pressure to compensate for gravity. And so this leads to a faster rate of hydrogen burning, so a shorter evolution. They evolve more rapidly. This means that if the same mass is lost during the RGB, evolved helium-rich stars should continue to have a lower mass when you see on the horizontal branch than stars that are helium-poor. And so they should be bluer when they are on the horizontal branch. Okay? So this explains the link between the sodium-oxygen anticorrelation that we have seen before and the variation of the position of the stars along the horizontal branch, so the second parameter effect. Okay, it came from here, from this variation in helium abundances. And this is the case of NGC 2808, in which Frank D'Antona in 2005, examining the horizontal branch, concluded that there should be at least three different populations with different helium, and the highest, the helium for the highest, for the most extreme horizontal branch stars should be very high, of the order of 0.35, 0.38, or 0.40, something of this kind. This was established simply looking at the horizontal branch. In the same year, this was 2 years later, Piotr et al. Discovered that the color magnitude diagram of NGC 2808, that there is one cluster in which there is no significant variation in the iron abundance. In this cluster, the main sequence, there are 3 sequences that you can see here. These are these are broadband colors. This is typical blue against an eye, so it's B minus I essentially, but you need the HST photometry to do this. And these 3 sequences, the stars in these three sequences can only be justified by a difference in helium, because The metal abundance is the same. No distinction in metal abundance. So there should be a difference in helium. Note that it is not a binary sequence because the binary sequence is on the other side. By the way, this population keeps about 50% of the total and the other 50%. And this is exactly what Frank has found from the horizontal branch. So this is a very nice result that you find the same thing from the horizontal branch and from the main sequence. But the horizontal branch, the difference in color of 1 magnitude at magnitude 15, 14, here the difference is 0.08 or 0.1 magnitude at the magnitude of 21. So the horizontal branch is a way to have a blow up on this difference. It's very sensitive to even small differences, while the main sequence is much less sensitive. The interpretation in terms of abundance of helium, helium 0.24 for the main sequence, the most populated one, 0.28 for this one, and 0.38 for this one. Very high helium. This, however, is about 25% of the stars in the cluster that have this high helium. Okay, so in 2012, 5 years later than before, we had gained a lot of information. The presence of multi-population is the rule for massive globular cluster. They are not present in low mass globular cluster. The absolute magnitude, of course, you should remember, is not the mass of the epoch of deformation, but this was likely larger than the present mass. And this may limit our understanding of what is the threshold for the formation of this mechanism. However, the limiting mass should be of the order of 2×10⁵, something of this kind. Other parameters may play a role: metallicity, concentration, and epoch of formation. Because in the diagram we have this correlation between age and mass that we have to remind. So maybe that also epoch formation may play a role. Helium abundance variation may be present, at least in some clusters, and there is a strong correlation with the second parameter effect on the horizontal branch. But we proceeded further. Okay, we begin to see more complicated issues in this pattern. The first complication comes from lithium. This plot in which I show the lithium abundance against the absolute magnitude for these are a compilation of globular clusters. This is the helium abundance in the main sequence star, the famous split plateau, the values which is slightly lower than is expected from cosmology, from Big Bang nucleosynthesis, but okay, this is for main sequence. Then you have a first drop that is due to this big penetration of the outer convective envelope that you have in the subgiant branch when you go from the main sequence to the subgiant branch, and tells you that the lithium is essentially destroyed below the in the inner regions of the star. This is because the temperature is high. And so you dilute the material that is preserved at the in the upper surface through all this envelope. And this is this first bump, and this is simply given by the ratio of mass that you have for the convective envelope in the main sequence and in the giant branch. Then there is another plateau, and then there is another fall down. This fall down happens at the bump, RGB bump, that I told you a couple of lectures ago. This change in the structure of the star that happens when the auto-propagating hydrogen shell burning meets the discontinuity that was left by the inner penetration of the convective envelope at the base of the subgiant branch. When this happens, there is no barrier for mixing, and the result is that there is a drop in the lithium because lithium is brought to regions where it is burnt. Lithium is easily burnt at temperature of the order of 2 million Kelvin, it is burnt. So this, we have, however, this intermediate region that can be very useful to compare different populations, because stars are bright, reasonably bright, and we can measure good lithium abundance in wide samples. And this has been done. And what it has been found is that if you plot this lithium abundance against the aluminum abundance, you find, okay, that when the aluminum abundance, primordial stars, is low, the aluminum abundance is low, primordial stars, the lithium abundance is about the one that is predicted for normal field halo stars. For the extreme stars, it seems that there is a depletion of lithium, but the problem is that for the intermediate stars, which are here, lithium is not strongly depleted. Okay? And how you can have this region here, while you expect that most of the possible polluters destroy lithium. For instance, if you consider as a polluter a fast-rotating massive star, this does not produce lithium. So they destroy completely lithium, actually. So the result is that these stars, if these were the polluters, these stars should be very low in lithium abundance. They are not. They have lithium. So this is one of the strong argument in favor of the AGB stars as the polluter, because the AGB stars are able to produce lithium. This is a characteristic which makes them different from massive stars. Another thing that has been done in the last years is to try to overcome the small number statistics that is typical of spectroscopic surveys. Some of the other 100 targets for each one of the cluster, using photometry. This is important if you want to understand if the population is divided into different groups, distinct groups, or it is a smooth distribution. And this has an impact on how we interpret the phenomenon and the mechanism that generated the sodium-oxygen anticorrelation. Actually, this is not done using sodium and oxygen, which are two difficult elements. So it is done essentially using nitrogen abundances. There is also a little bit of oxygen here, but essentially you are using nitrogen. They exploit the fact that there is a very strong nitrogen NH band at 3,400 angstrom that may give up to a strong absorption depending on the nitrogen abundance. If the nitrogen abundance is low, like in the primordial stars, the band is very weak. But if the nitrogen abundance is very high, that is what you obtain when you have the complete CNO cycle and transform oxygen into nitrogen, then the bands become very, very deep. And so you can split the stars into the two sequences, nitrogen poor and nitrogen rich, if you have a photometric system that exploits these. The other things that you can do is try to combine this with the determination of helium. Helium can be obtained from the general color. There is a temperature effect. The main sequence shift according to the helium abundance. But this requires observation of the main sequence. It's much more difficult than observing simply the nitrogen, which you can do also on the giants. So this was the idea, and there were a series of papers by Antonino Milone, by Giampaolo Piotto, and by others that show that this worked very well. The first example was the case of, I think this is 2808, in which they show that you may combine photometry in a lot of bands and having some idea about the helium variation and also the sodium oxygen variation. The helium variation is this general slope. The nitrogen abundance variation is this slope here, is this drop in these particular bands at about 3400. There is also a small drop at 3800 due to the CN band that we see from the ground also. So they constructed this kind of diagrams. They combined all this color to have the highest possible sensitivity, and the diagram were cleaned from all the field stars using proper motion. This is a very nice job because that has been done. And at the end, they end up with a diagram like this one. This is a magnitude, and this is a pseudo color where you can see the main sequence, the subgiant branch, the horizontal branch, which is here. And you see that, particularly in the subgiant branch, you can distinguish very clearly different sequences, which corresponds to different nitrogen abundances. And the difference is so large that requires that this difference in nitrogen abundance is actually a difference in oxygen abundance also. So you can use this number to make a much larger statistics than it is possible from spectroscopy to study the sodium-oxygen anticorrelation. Actually, to study, in this case, the nitrogen variation, abundance variation. And they prepared what is the Antonino called the chromosomic diagram. I don't like very much this term, but okay, he liked it. And so this diagram like this one is obtained by putting lines, fitting lines, to see the distance from the lines that you have on this diagram. And you find that the stars distribute not uniformly, but they populate particular groups. In this case, there is NGC 6723. In this cluster, you have a group that should have this composition of the field stars, so they call the first generation. And then there is the group of stars with enhanced nitrogen, which they call the second generation, 2G. Okay? I don't remember who was the name of the girl who presented the first day, exactly a diagram exactly like these ones. But it was from Chile, from Iberia. Okay, not a girl, a man. Okay. My memory is not good. Okay, so we use now this data also to make this kind of correlation that we obtain from the spectroscopy. And again, you find that there is a clear correlation here, for instance, between this parameter, which is essentially nitrogen abundance, the abundance of the nitrogen in the second generation, and the mass of the cluster. Okay? Which reproduce what we found with the interquartile for the oxygen-sodium abundance distribution. And this is based on a large sample of clusters, the order of 40, 50 clusters. Some of them overlaps with the cluster that we observe, some are others. But at the end, they confirm each other, all these results. So we are now very sure that the multiple populations are present in all globular clusters, so much that we can invert this consideration and say that the globular cluster is a cluster where we have the multiple sodium, the multiple population phenomena. If there is not, we may call open cluster. This is possibly a better definition than the vague term that is typically used. In many cases, especially using the photometry where the population are larger, we can clearly separate few discrete populations. And this is something which is not obvious. It's telling you something about the mechanism. You have really different groups of stars with different composition. It's not simply a smooth distribution. The separation between the multiple population are a function of metallicity and absolute magnitude. The fraction of first generation stars decrease with absolute magnitude. This is slightly different from what we obtained, but notice that in our definition of first generation, it is easy to have some second generation star that ends up to be counted as first generation. So this is a more precise result that has been obtained now. And large variations in helium are actually rare. In most globular clusters, the most helium-rich stars have Y of the order of 0.28, 0.29, 0.3. Values like 0.38 that we found for 2808 are rare. Only very massive cluster shows these very high helium abundances. Well, what are the polluters? Okay, they must experience hydrogen burning at high temperature. This is the very basic request for the polluters. But they should not have the triple alpha reactions, because there are no carbon stars in globular clusters, or at least very few of them, likely a binary evolution. The material should be given back to the interstellar medium at low speed, not to be lost from the globular cluster, and should possibly generate a cooling flow so that you have a mix of material from which you form a second generation, a group of stars, not simply that you form continuously stars from the material that is ejected by the star. You should avoid mixing with the supernova ejecta, at least in most of the cluster. So the time scale of production should be different, either before, that is less than 5 million years, or after, that is above 30 million years. In this interval of time, you have the supernova, the core collapse supernova, and you should avoid them. And at least for the I stars, which are the majority, they should produce lithium. Okay, the two most favorite mechanisms are intermediate star as fast rotating massive star. Intermediate mass AGB star are stars within the range of 5 or 4 to 8 solar masses, and we are considering them during the AGB phase, where there is hot bottom burning and there is also a lot of mass loss. And this fact that there is a lot of mass loss allows you to give back to the interstellar medium the material in the right moment. The advantages are that, okay, these stars do not produce iron, so no problem with a constant iron. Also, that time scale of evolution is longer than the core collapse supernovae, so from this point of view, okay. Can produce discrete values because they can generate cooling flows, are consistent with the idea that there are cooling flows. So the single star produces very small amount of mass, but if you have a lot of IGB stars altogether, they produce cooling flows. Can produce all the anticorrelations that are observed and also lithium. So from the point of view of chemistry, they are okay. They can all get to y equal 0.36. There has been a debate what is exactly the highest value of helium that you have in globular clusters. Values in the origin we derive value about 0.4, but now the value that is favored for the most helium-rich stars are about 0.38, so it's very close to this 0.36. Requires some tuning of the models, because if you do not make this, the models produce very odd abundances. In particular, you need a particular law for convection and mass law to produce the observed abundance pattern. The intermediate mass AGB stars are only a fraction of the total of the stars in the original population. And so if you want to form a population which is actually 2/3 of the stars of the cluster are formed from this, you need that there was a much larger population originally of primordial stars, and most of this primordial population should have been lost from the cluster. This is a requirement for this model. The order of magnitude is 5 to 10 larger.
Except the one that make the display.
This is a so-called mass budget problem. Okay, this is the production of lithium, okay. Then the other favorite mechanism is fast rotating massive stars. The idea is to consider very massive star. Mass is lost through a dense, low-velocity circumstellar disk. Actually, in the original model, they thought that the stars form around these primordial stars, the massive star, immediately in the disk. The time scale is much shorter, less than 10 to the 7 year. And this creates difficulties because it is very difficult to avoid variation in iron over age, because these stars evolve on the same time scale as the core collapse supernova. They may produce a lot of helium, no problem. They cannot produce aluminum and other elements that are found to vary in clusters. And this is a very big problem. The other thing is that it's difficult to reconcile this model with this scenario with cooling flows. And the result is that, okay, it's not easy to accept this mechanism. In any case, they have the same problem that we have for the other star, unless the mass function is very peculiar. Unless the first population only included very massive stars, and the second population only include low mass star, which is very constrained, there is a mass budget problem also for this, more or less similar to what we have to the GB stars. There are other polluters that have been proposed. Massive binaries, novae, supermassive stars. At the end, all of them have more or less the same problems. For instance, supermassive stars, you require an enormous number of very massive stars that are never been observed. The novae, okay, you require, again, an enormous number of novae, and also the novae lose to too much high speed. Massive binaries seems a variation of the model of the fast rotating massive star, and more or less the same problems. So all these models have problems. In general, the real problem is the mass budget. You require that the original object from which the globular cluster formed were 5 to 10 more massive than the current globular cluster. It is also possible that there are different polluters, because the properties of the intermediate star are slightly different from the properties of the extreme stars. So may think that, for instance, the intermediate stars comes from AGB star, while the extreme stars comes from fast rotating massive star. This is possible, too not very popular as an explanation. To explain the situation, the best current situation for the case of the AGB polluter, we can recall the paper by Franca D'Antona. Here is the temperature, maximum temperature that you experience during the AGB at the base of the convective envelope of the AGB, so the hot bottom burning, against the mass of the star. And you see that this is a function of the mass of the star. The highest the mass, the highest this temperature, and you may get to temperature high as 100 million Kelvin or even more. And in these stars, you may activate all the cycles that you need to explain the abundance. And this may quite well reproduce all the observed abundances. So this is the main advantage of this model. Her scenario is very complicated. She tried to explain various clusters using different mass of the polluters. Well, we said that there is this mass budget problem because it is a real problem. In principle, there is no reason why you cannot think that the cluster form in a much larger episode of star formation, and they are only a byproduct of this very big phenomenon? Well, the idea is that if you look at the dwarf galaxies, like Fornax, and there has been a paper also on WLM, and Wolf, a dwarf galaxy, and the idea is that if you look in there, you may count how many stars are in the field that can be the progeny, can be the first generation star from which the globular cluster formed. And the result is that essentially you find not enough stars there. Of course there is a problem, because this assumes that these galaxies did not lost star, which is absolutely not shown. So it is a requirement for these criteria to be definitive. So at the end, it's not an obstacle, but I would not say that it is not possible to reconcile with the observation. Another issue is that, okay, we have found that very massive cluster with mass larger than 10 to the 5 solar masses, have these different episode star formation that leads to the multiple population. Okay, why don't look at very young nearby objects and see if really we see this different population? There have been a lot of studies, mainly by the group by Nate Bastian and co-workers, trying to search for this evidence for this multiple population in young massive clusters. They are not in our galaxy. There is no such a big cluster in our galaxy. But if you go to other galaxies nearby, you can try to see if there is something. And they have done a lot of search, and they conclude that there is essentially no evidence for this second generation among all these clusters. From this point of view, the situation is quite unsatisfactory. It is not exactly clear if the mass is the same, because as I told you, the cluster change their mass during their life. So comparing the mass of cluster which are 13 billion years old with clusters that are now forming is not easy. So it may be that these clusters are not the local analogous of globular cluster, but still it's not nice that we do not find any evidence for this second generation around young massive objects. There has been a lot of discussion about clusters, populous clusters in the Large Magellanic Cloud and Small Magellanic Cloud. Essentially, the clusters with intermediate age, the order of 1 gigayear or so, or even less, are very well suited to study different populations, because in this case, the difference in age is perhaps enough large that you can see different turn-offs corresponding to the different ages of the different objects. So why not look at this cluster? And there have been many attempts, and the early ones found that there is a spread in color at the turn-off, or in magnitude, depends on how you look at it. And so this seemed a confirmation of this phenomenon. There was something strange, because if you use age to explain the difference between the spread that you found here, the age spread should be very large, of the order of several hundred million years, which is a little bit difficult to accept. Even the AGB phenomenon is in the AGB scenario, where the difference in age between the first generation and the second generation is largest. The age difference is of the order of 30, 50 million years, not hundreds of million years. So it is not easy to understand how you can keep the gas all this time in this old cluster. This was one problem. But for this reason, people look for other possible explanation and found a lot of possible explanation. The first thing is that there may be binaries. And the second thing is that it was found that there may be the effect of stellar rotation that widen this sequence. So they have begin to construct models and try to understand if, for instance, rotation or binaries can explain the spread that you have. There is also variability because in some cases you end up into instability strips like when examining these objects, so you must be careful about also variability. Okay, so all these effects can contribute to the width that you observe. And the result is that the age spread is still controversial, so there is a majority of people that thinks that there is no spread. And what you are really observing are all these evolutionary effects. Very recently, there has been another observation, now looking, this was again the group of Nate Bastian with other people, looking for populous cluster of intermediate age in the Magellanic Cloud. They used a variant of the Milone method to separate population using HST data. And they find that all clusters that are older, these are mainly these are LMC and SMC cluster, all clusters that are older than about 3, 4 something million years show the oxygen-sodium anticorrelation. These are all massive clusters with mass of the order of 10 to the 5 solar masses, while all the young ones do not show. So they suggest that there may be an age effect or something that is related to the mass of the star, which is about 1.5 solar masses here around. And that this is change the situation. For some reason, you can get the multiple population for the older in the older cluster, and you cannot get for the youngest one. There is a gap here, which is quite large. It's of the order of, these are 2 billion year, and these are 6, 7 billion year cluster. So this gap is quite large. But the other problem is that they interpret in this way, this dashed line. Young cluster do not have, old cluster have, and sodium, oxygen, so multiple population. But one can also interpret the diagram in this way, because this is more or less the fading of the clusters with age. And say that the young cluster are below this fading curve, and the old cluster are above, because these are more massive in origin, and these are less massive now. This is not fading, this is mass, but it's essentially the mass loss that you expect from the clusters. So everything depends on the interpretation of this single point. Okay? Because this single point is the only point which is clearly below this line, and so cannot be interpreted in this way. They argue that there is not important mass loss in the cluster of the Magellanic Clouds, which can be questioned a little bit. But the other point is that the observation is this object here. And while I would say that, for instance, here there is a clear evidence of splitting of the sequence, the evidence here is not so obvious. And for the moment, I would say that making big conclusion based on simply the appearance of this diagram is a little bit dangerous. Okay, I think I am in the last 2 view graphs. 3. Okay, there have been other scenarios for the formation of globular cluster at the multiple population. Very recently, there was a paper by Bruce Elmegren. The idea there is that interaction between massive stars and massive star binaries can shred stellar envelopes in a very dense environment. And in addition, this mechanism should also scatter low mass stars out of the cluster. So this may help to explain why there are some few first generation stars in a cluster. He finds that there is agreement with observation if you assume a core mass of the order 4 × 10⁶ solar masses and a very high density, 2 × 10⁶ atoms per cubic centimeter, which is extremely high density. And the idea is that this mechanism is efficient at early epochs when the pressure was higher, and this can explain clusters, and also can explain why you don't you observe these field stars in the Fornax and WLM galaxy, because the idea is that the ejection of the low mass stars is so efficient that they are lost by the galaxies, by the dwarf galaxies. So this is an attempt to explain everything. I think that the more nice idea for me, my favorite idea, is the scenario that is now being proposed by Becky. Okay, the idea is that you have a dwarf disk galaxy. In this dwarf disk galaxy, you have a very giant molecular cloud that begin to form a lot of clusters. You have a larger cluster in some position and a lot of smaller clusters spread around. And the idea is that in this kind of object, you can have that the main cluster will form later the globular cluster, but can acquire material AGB ejecta not only from the stars that are in the cluster itself, but also from all the population that is here around. Okay, at least a large fraction of the AGB ejecta of all this population may end up in the main cluster, which is at the center. Okay? Then you have dynamical evolution of all these things, and at the end you end up with a globular cluster with two populations. Okay? He started from distribution of clusters using the typical distribution of cluster that you find in star-forming regions, power like -1.7, as I told in the first yesterday. And he generates random distribution, this is with these characteristics, and he looks at what happens for the accretion of the mass from the object, because the central object, which is more massive than all the others, may accrete the low velocity ejecta from all these stars. And this may contribute, may go to the center, making a cooling flow, and then you have the second generation of stars. So this is a variant of the model that has been proposed previously by D'Ercole et al. But the variation here is that you include mass that come from all these big association that is of cluster that is around the original one. And in this way, possibly you can solve this issue of the mass budget problem. Of course, the assumption is that the region of star formation that you start from is enormous. It's not 2 × 10⁵ like the current cluster, but as a mass that is at least an order of magnitude larger, at least 2 × 10⁶ or even more solar masses. So this is a much scaling up of the object that helps to solve the mass budget ratio. Okay, this is the last biograph.
Is it possible that the clusters present a self-enrichment in lithium due to the spallation when the stars are still forming before the second generation of the intermediate stars form?
installation will produce mainly beryllium, will produce also some lithium. Well, maybe. I cannot exclude completely. I have to, some computations should be made. Because of course the cosmic rays that are in the high energy hydrogen, oxygenators and so on that are required for this may be perhaps provided by the core collapse supernova in the environment. So it's difficult to model because you must do assumption how these flow up through the medium from which the second generation form. So it's not easy. But in principle, maybe. But you have this, but not the iron. Okay, so some difficulty there.
Okay, let me see if I can formulate what I'm thinking. These different populations have about what difference in age between them?
Much smaller than the age of the cluster. That is, the cluster has an age of 13 billion years. The difference, they are not distinguishable from this point of view.
Okay.
However, depends on the model that you assume. If you consider massive star, the difference is very small, less than 10 million years. If you assume that the correct model is AGB star, the difference is about 30 million, from 30 million to 100 million years, because this is the time, the evolutionary time for 4 to 8 solar massive stars.
Yeah, because what I'm thinking is that there seems to be a mass factor because of that division between massive globular clusters or luminous globular clusters having multiple populations and the smaller ones not having. So, but the smaller ones are old enough that if they were going to have multiple populations, they would have formed them already. So, yeah, I'm not sure I understand either. Let me try to think again. No, it's just that I'm curious about, we have open clusters without multiple populations, including old open clusters. Then we have not very massive globular clusters without multiple populations either, and then the massive ones with multiple populations. So it seems that it has, the mechanism has to necessarily involve age, not only the potential or the size.
I don't think it's in this moment strictly required. Maybe that age is an important parameter, but some of the clusters in the Magellanic Cloud where the splitting population has been found have an age of about 7-8 gigayears. Okay, so they are not really at the cosmological age. Okay, they are a little bit younger. Okay, so if age is important, the transition occurs at an age from formation of about 5 to 6 gigayears. Not very, very early in the history of galaxy evolution, okay, in some later phase. There has been a suggestion that there may be a role played somewhere by the temperature of the microwave background, which also evolved with time, of course. But it's not clear what is the real effect. In the sense that if the temperature was too low, you do not have this effect. But how it works is not extremely clear. It has to do with the cooling of the material, of the interstellar material.
In fact, I have a question. I'll give it to you in a minute. But I think that it's related with this one. You said that there is a second parameter, that it's the concentration of the stars in the clusters, yeah? And if I understood well your first lessons, this factor, the concentration, is a factor of the age of the cluster as well, no? Because you had those infants that disappear quickly, poor guys. And then you have the others that are older, and then, so, and it would be much spread. So I cannot really understand to put all these arguments together.
Concentration changes a lot during the life of a cluster. It evolves and comes and goes, so it's a little bit complicated. It's not easy to relate the current concentration with the original one. It's not easy. Okay, but it depends very likely also on the position in the galaxy where you look. But this may be a selection effect on the other hand, because you may have lost the low concentration cluster that are in the inner part of the galaxy. So in this diagram there may be also selection effects. That is, you do not observe clusters that have low concentration, that are in the central part, that are massive, because these are destroyed. And so, okay, you say there is this trend with concentration at the end. So it's a bit dangerous to extract from what we observe now what was at the beginning.
I think that there is a question.
Yes, I have two questions. The first one is related with this separation in three groups, the primordial, intermediate, and extreme. And I didn't understand why working with three different groups, because, for example, in some of the plots, I could imagine that the anticorrelation looks like a bilinear relation. So what happens if I separate the stars in the plot in just two groups, considering the difference in the slopes, and how results all the comparison with lithium and all the derivative comparisons that you made, if they are blurred or if they continue existing?
The division in three populations is completely arbitrary, and it's only in a way to separate objects that have extreme compositions from objects that are more intermediate ones between this extreme and the normal one, the halo one, I would say, the halo-like one. So the only purpose is this one, and can be misleading. I fully agree. In some cases, you must use with a lot of care. Essentially, the use that we do of this is to say that these extreme cases, which essentially means objects that have an almost pure polluter composition. Okay, this is the meaning, the real meaning of this object. Have other properties. Okay, then I agree that you must take it with care, and you may divide in another way. If you would want to use the separation between the spread, okay, can do, but this is already contained in interquartile. So, okay, this is another way to see the effect that it's been already explored. So.
And the other one is that when you show the plot of concentration against the residuals of the correlation between absolute magnitude and the anticorrelation length, I would like to know which could be the motivation of the existence of this plot, because it looks very clear the plot, the positions of the global clusters, but I have a doubt that the anticorrelation proceeds from the star formation episodes, who are very short in the life of the global clusters, but the evolution of the concentration and the absolute magnitude are more, they have a larger time scale, and they are very, they suffer the environment processes. So why should exist this this very nice correlation in that?
I actually do not think too much about this particular correlation. However, as I told before, selection effects may be important. That is, you may simply keep out from the diagram objects because this is an almost forbidden region. I mean, a region, for instance, which you have a very extended cluster, very low concentrated cluster, and of low mass, these are dissolved with time. And so you must be careful to what can survive 13 billion years and what cannot. Also, there is a general correlation in our galaxy of concentration with distance from the center of the galaxy. This is due to the dynamical evolution imposed by the galaxy itself. So clusters that are closer to the center are much more concentrated than clusters that are far from the center.
And sorry, in the Becky scenario, I assume that there is some there is like a fight. It's not a fight, the war, but like a competition between the I assume between the accretion of gas from the environment outside the global clusters and the ejecta of gas from supernova and the ejecta or the outflow produced by the supernovae in the global cluster itself, and how that make the variation of the mass accretion in the global cluster, of the mass growth in the global cluster with the time.
This is an important issue. It's not well. On one side, the mechanism is thought to be active only after the end of the supernova phase for the primordial population. Okay, so you simply start from there, from the end of the but then you expect that the new star formation episode, the ones that lead to the second generation star, do also lead to new supernova explosions. And these also should stop the formation of second generation star in some moment. Typically, these models that are based on the AGB stars include also a mass function for the second generation, which is cut at the largest masses, so that they have not the high mass object. Okay? How much is this reasonable is a matter of discussion. And actually, this Becky paper is the first of a series, and he says that in the second paper of this series, he will explore this point and show how he obtained this idea, but the paper has not yet been published, so I do not know his idea about this. In the Dercole model, it's arbitrary. They simply say they do not form massive second-generation stars. For the moment, I have no good explanation why there should not be very massive object in the second generation.
More questions? If not, our speaker.
Yeah, so just a few announcements. We are going to be taking the